Hi, this is Justin Charles Amor, a junior structural engineer of Global Estate Resource Incorporated. I'm here today to discuss the reinforced concrete design of an irregular concrete water retaining structure using MIDAS Gen. So, for today's discussion, here are the contents. First, project description. Second, modeling. So, these are the techniques that we're going to use to produce a 3D model in MIDAS Gen. Third, compression-only springs. So these are the boundary conditions that we're going to use to simulate actual soil conditions. Fourth, hydrodynamic loads. So these are the effect of slushing of liquid decreases under earthquake. And fifth, converting load combination to load cases. So this is a feature of MyJustGen that we'll be going to use in this discussion. The sixth is results checking. And the last one is mesh design. So here are the contents of our discussion for today. First, project description. So our case study will be a 15,000 gallon water tank, 5 meter in height, in which the water level is 4 meters, and it is located at General Mariano Alvarez, Cavite. So you can see at the right picture is a screenshot from a Google Maps. So this will be the location of the water tank, and the other one is from the Valley Fault System Atlas. So this atlas shows where the fault lines in Metro Manila are located. So if we superimpose the two, we can see that the location of the water tank is very close. It is 50 meters away from the fault line. Now that we have a brief knowledge on the project, we will now go to modeling. So at present, we know that the design softwares have the capability to import 3D models that are created using CAD softwares like AutoCAD directly into the design software. So there's an easier way to make the models and the design. But if you're using a CAD software that can only generate 2D models, well, there's no problem because Midas Gen has a feature that will help us create models, 3D models easily. So what we need is a DXF file of the footprint of our building, or in this case, the regular water tank. This footprint can be imported to MidasGen. So even it is a 2D model, we can import it. So whatever dimension we use, we'll be having it in the MidasGen also. Afterwards, we're going to use the extrude function. So this function is very helpful, especially in modeling in MidasGen. So we can use this to create walls out of that tank footprint that we imported into MidasGen. Now, for the slab, we can use the AutoMesh function of MidasGen. So, using this AutoMesh function, we can just go and select the boundaries of our slab. Then we can easily create the top slab or the bottom slab of the structure. In addition, since we are also going to mesh the walls, we can also mesh it using this function. Now, to show you how to do that, we're going to open MidasGen, then go to File, then go to Import, then click on AutoCAD DXF file, then select Browse. Then afterwards, you go to where our DXF file is, so wherever it is located. Then you select this tank footprint DXF file, then click Open. Then afterwards, you select the layer in which the tank layout is. So in my DXF file, I use the tank layout layer. Then, before pressing OK, you need to make sure that whatever the dimension we used in creating the footprint should be the same dimension we have in MidasGen. So in which case I used mm. So change it to mm first, then select OK. And now we've imported our tank footprint. Now, to create the walls, what we're going to do is we'll use this extrude function of MidasGen. So go to node element, then select the extrude function, then change extrude type to line element, then So we will define the extrude distance, so which in this case is 5 meter along the z direction. Then we're going to select the line elements, then select apply. Now we have already created the walls of the structure. The next thing we're going to do is to create the slab, the top slab. So we're going to use the auto mesh function, then change the method to nodes. After that, select the outer nodes of the top slab. Then change the mesh size to 0.5 meter and select apply. Now we have created the top slab. We're going to use the same method in creating the bottom slab. In this case, make sure that in creating the slab or in selecting the nodes, you should select it counterclockwise to make sure that the z direction of the plane will be upwards. So if you notice, both top and bottom slab are created by selecting the nodes in counterclockwise direction. So now that we have created the top and bottom slab, I'm going to use the planar element method to create the mesh of walls. So we're using the same mesh size, then select apply. Now we have created the 3D model and MIDAS gen. Now for the design criteria, so the codes and standards I used in designing the water tank is NSCP 2010, ACI 318, ACI 350, and ACI 350.3. So the ACI 350.3 is the seismic design of liquid containing structures. So this code on the material properties, the concrete is a 4000 psi compressive strength. Then for the reinforcing steel, there is a 415 MPa for 16 mm diameter and above, and 275 MPa for 12 mm diameter and below. Now for the boundary condition, we're going to use a compression only surface spring. So using this, we're going to imitate and simulate the actual soil condition. So we're going to apply the compression only soil spring on the bottom slab of the water tank, since that's where the soil is located. So to create the soil spring, we need the module for subgrade reaction. To compute for this, we're going to use an empirical formula. So Ks is equal to 40 times the factor of safety multiplied by the allowable bearing capacity. So this formula is found in a book of Bowles. So using this formula, I used a factor of safety of 3 and an allowable bearing capacity of 150 kilonewton per meter squared, which is equal to 18,000 kilonewton per meter cube for modulus of subgrade reaction. But be warned when using compression only soil springs. So when using this, we need to take special steps to ensure that the analysis will give us proper results, because if we don't do this, we are going to have convergence error in our analysis. So this special step, or this additional step, I will discuss it later. So now, to apply soil springs to the structure, so let's go to boundary, select surface spring, then distributed spring, and change the type to planar face, the spring property type to compression only, and our computed modulus of subgrade reaction of 18,000 kilonewton per meter cube. Now we're going to select the bottom slab, then select apply. So if we want to see if it really is applied, you can go to Trim menu, Works tab, then go to the boundaries, right click on the planar face, compression spring, then display. So as you can see, you have already applied the salt spring at the bottom slab of the water tank. Now our design loads. So we have a gravity load, dead load, and live load. Then also have a hydrostatic load, which is from the height of liquid of 4 meters. Then we also have a seismic load. So here are the seismic parameters that we're going to use to compute for the following. Hydrodynamic pressures, both impulsive and convective components. So these hydrodynamic pressures are a result of the sloshing of liquid inside the water tank during an earthquake. The next one would be effect of vertical acceleration. So due to this acceleration, it increases the applied pressure of the water on the walls of the tanks. Then the next is the inertia forces of the structure, the slab, and the wall. So in a regular tank, the impulsive and convective components of hydrodynamic pressure are influenced by the ratio of the length of a chamber of water tank parallel to the seismic force to the height of the liquid in that chamber. So if you want to get an accurate values for the loads to be applied on the structure, we need to properly determine the length that the water will travel in the chamber. So for an irregular water tank, it's not easy for us to determine which values of L to be used. Of course, if you use the longest value for L, you may not be able to get an economical design, which we are avoiding. So to get the proper values of L to be used, we need to determine the following. So we need to determine the direction of earthquake, which will give us the highest seismic force. So how are we going to use to find it? We need to find the excitation angle of the structure. Now how do we find this excitation angle? We're going to use the response spectrum data. So to create this response spectrum data, there are two steps. The first step is to create an RS function. So we need to determine the design spectrum using these parameters. Then after defining the RS function, we're also going to define the RS load case. So we're going to create an RS along major direction, along orthogonal direction, as well as the vertical direction. Now, what is excitation angle? Excitation angle is the angle from the x-axis in which the earthquake, the direction of the earthquake, would give the high seismic force to the structure. So, I'll show you how we get the excitation angle. First, we're going to the load tab, then dynamic loads. First, select the RS function, then click add. Then we'll define the design spectrum. So we'll use UBC 1997. Soil profile type SD. Seismic zone factor 0.4. And the distance would be 0.05 kilometers. Then click OK. After creating the design spectrum, click another OK and close. Then select the RS load case. So we'll create a load case RS major. Then click the auto search angle, allow major. Scale factor of I over R, which I is equal to 1 and R is equal to 4.5. Then check the UBC 1997, then add. Also going to create one for orthogonal direction. So RS ortho. Then click ortho for auto search angle. Then click add. Then going to create RS vertical direction. Then select the direction to Z. Then same scale factor. Then add. Then after creating the RS function, you can now run the analysis. So after analysis, what we're going to do is to check first the vibration mode shape of the structure. So we're going to check if the mass participation factor of the structure exceeds 90% for all directions. Then afterwards, if the percentage of mass participation exceeds 90%, you can now use the response spectrum data. We're going to check first the excitation angle. Then afterwards, we're going to use the response spectrum data, convert it to nodal loads. Now that the analysis is done, you can now check first the vibration mode shape. So to do that, I'm going to select results, then vibration mode shapes. Then I'm going to check the mass participation percentage if it exceeds 90% for all directions. So as you can see, the mass participation percentage exceeds 90% for all three directions. Now we can use the data. First, we're going to go to the RS load cases. You can see the excitation angle, which is 28 degrees. So now we know the excitation angle of the structure. So this excitation angle defines the direction of the earthquake force that will give the highest seismic effect on the structure. So the convective and impulsive component of hydrodynamic loads can be computed using these formulas, which you can see in ACI 350.3-06. These hydrodynamic loads can be linearly approximated using the following formulas. So instead of having the exact distribution, which is a curve distribution, you can use this linear approximation. Now, how do we determine this hydrodynamic load? First, we would select a wall. Now, this wall, we'll divide it into subsections. In this project, use 3 subsections, but you can use a higher number or amount, maybe 4 or 5, to increase the accuracy of the loads that you will going to apply. The next, we get the distance of these subsections to the immediate wall parallel to the direction of the seismic force. Then afterwards, we're going to find the mean of adjacent lengths of an intermediate walls. So we'll find the average in these subsections. For example, in this middle section, we average at 2031 and 4061 mm. So the average would be 3.046. So we did that for the 3 subsections. Then after getting this average distances, we know that, and since the direction of the seismic force is not perpendicular to this wall that we have previously chosen, we need to first determine the angle between the line perpendicular to the wall and the direction of the excitation angle. So as you can see, the gray line shows the direction which is perpendicular to the wall, and the red line shows the direction of the excitation angle. So these two lines have an angle between them of 7.540 degrees. So we're going to use angle to determine the actual pressure that is applied to the wall. So we're going to do this for all the walls. What did I do for the curved wall? What I did was I divided the wall into 4 parts. So it's still the same procedure, but its difference between the straight wall would be it has varying angles. It means that you cannot use the same angle for all sections of the curved wall. Now, after applying the hydrodynamic loads on the walls of the structure, now from the results of the response spectrum data, we can get the nodal acceleration, the maximum dz, should be equivalent to u sub v. So this value will be multiplied to the hydrostatic pressure for us to get the effect of vertical acceleration on the structure. Now for the nodal results of RS, on RS major and RS ortho, we'll convert these inertia forces into static loads so that we will be able to add it into our analysis later on. So how do we do this? Click the nodal results of RS. Then first check the RS vertical. Now what we are interested in this is the nodal acceleration. So we're going to determine the highest value of dz. So to do that, we right click, then click sorting dialog, then click on dz, then move its priority to the highest, then sort. So as you can see, the highest value is 3.23. So this value will be our multiplier later on for the effect of vertical acceleration. Now, after getting the maximum value, we're going to convert now the RS major and RS ortho. So check the RS major, then to convert it to nodal loads, just right click, then select the convert to nodal load. After that, make sure that RS major is checked, then select the predetermined load case. So it means that before converting it, we need to make sure that before analysis we already have this load case. Then okay, yes. So as you can see, this is the converted nodal loads. So from the response spectrum data we got earlier, here are the loads applied to every node in the structure. Now, for applying the effect of vertical acceleration, we'll first go to load combination, then create a load combination for this. So let's type in vertical, then select F. So this F is the static load case for the hydrostatic loads we applied on the wall of the water tank. Then for the factor, use 3.23 and OK. Then afterwards, we go to using load combination, select vertical, then apply. So after applying, now we can check this. So now we can see this is the hydrostatic load applied. So when you increased it, we use the converting to nodal load cases. So here's the magnified load. So instead of applying it again to the wall, we just use the easiest way, which is converting load combination to load case. Now for structural analysis and evaluation. So this is a tank at rest. So when we apply gravity loads, of course, the soil is bound to resist the gravity loads. And by doing this, the soil undergoes compression. Now, when a lateral load is applied to the tank, of course, there's a possibility that it will overturn. So when the tank lifts, the soil will not be able to resist its lifting motion because the soil cannot undergo tension. But we know that in actual condition that gravity loads and seismic load does not exist separately. So they are applied to the structure at the same time. So how do we imitate this? So to imitate this, we use converting load combination to load cases. So in doing this, both gravity loads and lateral loads are applied to the structure at the same time. So when the MIDAS gen runs analysis, it considers that both loads are applied to the structure at the same time. How do you do this? First step would be you select the using load combination. Second, we select the load combinations that we're going to convert. Then click apply. So after applying, this load combination will be instantly converted into load cases, static load cases, not just load combination, so that during analysis, MIDAS Gen would consider this as existing at the same time. Now, after converting load combination to load cases, you can now run the analysis. So, another special feature of MIDAS Gen is being able to check the soil pressure that the structure has. So how do we check soil pressure? So first, we must activate first the bottom slab so it's easier to check the results. Then go to results tab. then reactions, then soil pressure, then tag apply. So this is the soil bearing capacity. As you can see, it varies in different locations. So if you're going to check the maximum bearing capacity or the maximum soil pressure is 142 kilopascal. So it is the maximum soil pressure is less than the allowable bearing capacity that the soil can handle. Means that the soil is stable. So what if the maximum soil pressure exceeds the allowable bearing capacity? What we're going to do is we're going to increase the bottom slab so to be able to dissipate the load in a larger area. So doing this will lessen the soil pressure that the structure is giving. So after checking soil pressure, you can now go to the slab wall design. So in slab wall design, there are two methods that you can do. The first one would be we extract the design forces from analysis. Then after extracting in, you can do manual design, either Excel spreadsheets or manual calculations or other design softwares. The second one is a mesh slab wall design. So this mesh slab wall design is what I used in designing this concrete water tank. So in mesh design, we are first going to select the criteria for rebars, the possible rebars that we're going to use, the concrete cover, the spacing. Then this is what it looks like when we design it. So it defines the rebar per placement. How did I do the mesh slab design? So we're going to show you now. So we're going to use the bottom slab for the mesh slab design. Now what we're going to do is go to design, go to the slab flexural design, select average nodal. Then for this presentation, we're going to design the top bar along direction 1. So direction 1 is parallel to x direction. Now this is the rebars that we're getting. Of course, if we put rebars like that, it's going to be hard since it's uneven. And also, using the highest value, which is 25 at 100 to the whole slab, is not economical either. So what are we going to do? Now what we can do is, and what I did was I selected the rebar spacing that is mostly applied in the whole structure. So I used the 20 at 200. Now how do I do that? So we go to the domain, right click, then properties. Then we check the basic rebar for slab and mat. And since we're designing the top direction 1, so we're going to change it to 20 at 200. Then modify. Now we go again to slab flexural design. Then apply. So now as you can see, if you apply reinforcement of 20 at 200 to the whole structure, we're going to have an additional rebar according to what's given here at the results. So for the green one, we add an additional 20 at 200. Then for the yellow one, the red one, respective to the what's given in the design. So of course, we can manipulate the angle or the direction of the rebar that you might be able to provide an easier way of reinforcing the slab. So for example, what if the direction 1 of the reinforcement is parallel to the longest wall? So how we're going to adjust that? To adjust that, we'll go to the domain, right click, then properties, and change the direction 1 angle. So the direction 1 angle should be the same as the longest wall, which is 135 degrees. Then select modify, then close. Now we'll run the design again. So select apply. Now as you can see, changing it makes the additional rebars to be easily added. So the amount of additional rebars is reduced. It can only have to add rebars at the curved wall and at the bottom corner of the water tank. So this is how I did the mesh slab design. In conclusion, MIDAS is very helpful in our design, especially in our projects in global estate. It can easily give us solutions, analysis, can easily run studies on different projects or problems we encounter, can provide information, results. It can easily provide the example, the soil bearing capacity, the soil pressures that these structures apply to the soil. I mean, there's a lot of different features of MIDAS that helps us in our work here in global estate. And it's like you can do a lot of things with just the MIDAS gen as long as you know the different features that MIDAS gen have. As long as you can properly use it, you can do anything that you need to do. That's all for the discussion. Thank you very much.